Good afternoon and welcome to the 18th Annual Schnabel Engineering Lecture. My role here is very brief. I would like to welcome you here to Virginia Tech and to welcome Alan Cadden. Alan Cadden is Principal of Schnabel Engineering and a very good personal friend and a very good friend of our program. Alan.
Thank you, Adrian. Good afternoon. I'm happy to be able to introduce the 18th Schnabel Engineering Lecture here at Virginia Tech, especially at a time when the civil engineering profession is exploding and the infrastructure opportunities and environmental needs will provide excitement and many real challenges throughout your careers. We couldn't present this lecture without the help of Dr. Rodriguez and Mrs. Atwell, as they do the hard work of making all the arrangements here on campus. We at Schnabel love this opportunity to return to Virginia Tech each year and host this event. So we thank you for welcoming us back. Some of you may know this, but Schnabel is approaching 70 years old, or young, depending on your perspective. We have about 30 offices across the country, and from these locations, we offer services throughout the United States and around the world. We're excited to have announced that JCK Underground joined the Schnabel team at the beginning of the month, which significantly increased the size of our underground engineering and program management group. We're a 100% employee-owned company. It's an ESOP, and over our nearly 70 years of history, we have grown in breadth of services as well as geography, growing from a traditional geotechnical engineering start to a much broader design firm, now including full services around specialty foundations, dams, and tunnels. For me, some of the most exciting new work involves applications of innovation around data science, digital twins, and advanced visualization within our workflows. Given the challenges we face today and the opportunities we see in the future, we host this lecture each year to bring you a different face of our profession from outside the academic halls. These lectures, many of them recorded and available in your library, present different aspects of a career in civil engineering. Careers that have evolved over decades. They share their stories. They also do a little pontificating on what you might see as your careers evolve. Today, we bring you a colleague and a friend of Schnabel. Recently, I have had the pleasure to work with Dave as a Deep Foundation Institute trustee. So without further ado, let me introduce our speaker for today. David Paul, professional engineer, is the managing partner of Paul Geotech Engineering, LLC in Denver, Colorado. He retired from the Corps of Engineers after 22 years of federal service as a dam safety officer for the Mosul Dam Task Force, which provided technical assistance to the government of Iraq to mitigate dam safety issues associated with the Mosul Dam, a fascinating case history in itself for geotechnical engineers. He also served as a special assistant for dam safety at the Corps of Engineers headquarters in Washington, D.C., responsible for managing the Corps' portfolio of 715 dams. He is a national specialist on critical infrastructure design, dam design, levee design, construction engineering, engineering risk management, interim risk reduction measures, and dam and levee safety modifications. He was a geotechnical subject matter expert for the Oroville Dam Risk Assessment in California, which is the tallest earth dam in the United States. He has been involved in the design and construction of 11 new dams and over 75 dam modifications around the world. As I noted, Dave is currently a trustee of the Deep Foundation Institute and a member of the Association of State Dam Safety Officials and American Society of Civil Engineers. In addition, as a member of the United States Society on Dams, he serves as the co-chairman of the USSD Committee on Construction and is active with the Embankment Dam Committee. He is also the USSD representative to the International Commission on Large Dams, ICOLD, in Embankment Dam Committee. So please join me in welcoming Dave Paul to Virginia Tech. And Dave, we look forward to your insights on the history of dam and levee safety in the United States. Thank you. Welcome.
Thank you, Alan, for the kind words of introduction. I sincerely honored to be invited to come today and enjoy the beautiful weather, the beautiful campus here in Blacksburg, and be able to come and speak to you on behalf of Schnabel and Virginia Tech University. So Alan emphasized to me when he invited me that he wasn't interested in a technical lecture. So I definitely took him at his word, and I assure you that the content and my words today are definitely not technically oriented, but nonetheless, I hope that you find it interesting for your career paths. So the presentation topics that I'm going to cover, I'm going to talk about Fontenelle Dam, which I don't think many of you have ever heard. So precursor to Teton Dam, and talk about the development of dam and levee safety programs in the United States, and talk about how it impacts infrastructure, and as the profession migrates towards risk-informed decision-making in administering those programs. So I felt compelled, I need to, I think, give a bit of carbon dating for myself to you all. So as Alan said, my career has been federal. So started with the Soil Conservation Service in Illinois in 1976, went to Denver, Colorado to work with the Bureau of Reclamation after Teton Dam failure in 1978, worked there 32 years, then finished up 8 years with the Army Corps of Engineers as they stood up their risk management center. So when I started, 78, there were no cell phones, there were no laptops, there were no computers. So we had one rotary dial phone for 5 people. You could smoke at your desk. So all drawings were done by hand on linen in a huge room. There were 100 oak drafting tables filled with World War II Korean veterans who smoked, and the work and the drawings that they created were truly pieces of art, but everything was done by hand. All memos were written longhand and taken to the steno pool, and 25 ladies with typewriters typed out your memos. So that's carbon dating myself. And we ran stability analysis from computer punch cards and took them down to the computer room and slid them through the window to run on the IBM. And an hour later, go back and hope that you had some output and didn't have an incorrect card. So my point being, the amount of technology and transformation that's happened in my professional career, when I pause and reflect on it, truly just blows me away. So you are all, to me, in this world where technology is changing rapidly, and frankly, it's hard to keep up sometimes, but embrace it. It's just unbelievable what you can do these days with the power of computer and communications technology. So my professional career is rooted with the failure of Teton Dam that failed June 5th, 1976, Teton River in Idaho. Designed, constructed by the Bureau of Reclamation. As a result of this incident, the organization underwent a very rigorous, robust evaluation by independent expert engineers brought to bear by the U.S. government to investigate the accident. I have dear friends that were involved with the design construction of Teton, and they were there throughout construction, and they're standing up by the left abutment or the right abutment at the spillway when the dam crest fell in. So they were there that morning, started around 6:30 in the morning, progressed quite rapidly to the failure at around 11:30. So working for Reclamation in 77 and 78, they hired about 500 of young engineers from around the country. We repopulated the Technical Service Center in Denver and reestablished the organization. From that, they created the actual dam safety office within the Bureau of Reclamation. I was asked in October 78, 45 years ago, by Rich Kramer, who was running the organization, Embankment Dams Group at the time. We're opening up the dam safety office. Dave, we need some help. Would you take some time and volunteer and help? And I said, sure. And I did so. And so I've been immersed with dam safety, dam engineering, construction my entire career. So it's, again, fundamentally rooted in Teton Dam failure. Had the great fortune to be blessed to have many engagements with Dr. Peck over my career. He served on several consulting boards for dams that I designed and constructed. This is his quote with respect to the failure at Teton. Frankly, if you're have interest in the dam levee world, I submit reading those proceedings from that investigation should be required reading. I'm sure you can find it online. Again, had good fortune to be involved, talk to Dr. Peck and others that were involved with the failure. The state of the profession at that time truly should have dealt with the geologic conditions that presented themselves at Teton. There was truly a situation where the organization failed, quite frankly. So before Teton, there was actually Fontenelle Dam on the Green River in Wyoming, western Wyoming. Earth dam, about 150 feet tall, 5,000 foot crest length, built in the 60s. And frankly, it could have been, instead of Teton Dam, could have been Fontenelle Dam in the 60s. So this is a picture of the foundation. There were vertical joints, open joints, very problematic geologic conditions upon which to build an embankment dam. The design here, you can see some of the open joints. There was generally not a rigorous cleanup program or treatment program, and the single line of defense to mitigate foundation seepage was foundation grouting. A fairly conservative section in terms of the impervious barrier, the impervious core, constructed out of silt and gravelly silt, similar to Teton. Upon first filling, you can see the amount of seepage that manifested and reflected itself along the downstream toe. It was not expected, as you can probably appreciate. But what really caused the incident or the concern is this is May of 65. The spillway is constructed over on the right abutment. This is the spillway embankment contact. Again, some of the pictures that I showed showing the irregularities and open joints in the foundation, seepage migrated through, created erosion, and there was a near failure here. This was, they were able to open the gates, lower the reservoir, and establish safe condition. They then excavated this, backfilled it, reconstructed, refilled the reservoir, and lo and behold, in July, a second event happened. So you can see the extent of it in the same general area. So again, just a few months, the same event happened again, emergency evacuation, lowered the pool, excavated this out, and rebuilt it, reestablished the reservoir pool, and lo and behold, there was a third incident that occurred in September of 65, much larger in extent. When I see these pictures, I am constantly amazed that the crest didn't fall in and the dam breach, causing release of reservoirs. Just a miracle that it didn't happen. So they excavated and rebuilt this section and reestablished the reservoir. So I point this out in that if you work for large organizations, you shouldn't be complacent. So you should guard against being complacent. The Bureau of Reclamation had built Hoover Dam, Glen Canyon, Grand Coulee Dam. So there was, in all honesty, some arrogance within the organization, having all of those grand dams in their portfolio, operating successful around the West. In response to this incident, reclamation designers and managers heard about Fontenelle, but there was, in talking to engineers working in that era, they heard about it, but there was not widespread discussion, presentation, or conversations about cause and extent. So this is truly before a formal dam safety program was designed and implemented. So moving on, and again, from Teton, 11 lives were lost. The dam was essentially topped out and failed upon first filling. And again, the state of the profession, in all honesty, if you go back to that era, the state of the profession was mature and certainly had the experience and the wherewithal to be able to treat a difficult foundation. This was volcanic basalt, lots of open joints, but again, the organization did not really heed the state of the practice, and lo and behold, the dam failed on first fill. So again, some of the lessons learned. The principal designer for the dam in Denver visited the site one time during construction. One time. There was essentially little to no coordination or communication between the construction team building the dam and the design team that designed it in the Denver office. There was no external review, no consultant boards at that time. And again, the primary defense against seepage through foundation defects, which were significant at this site, was essentially relying on a single line grout curtain. So moving on to, again, the history as it relates to dams as a significant piece of our infrastructure in this country. So where there's dams, there's dam failures. So I'll talk here in a minute about the NID, the National Inventory of Dams. So in the United States of America, there are 90,500 dams in the NID, which I continue to find as an astounding number of dams that have been built and are registered in the NID, which is administered by the Corps of Engineers. So again, you can see with the NID, the federal government, the Corps of Engineers, Bureau of Reclamation, TVA has been able to keep track of failures or incidents which have generated these statistics. So there's low probability, but nonetheless, when you impound water and create a lot of potential energy, if you don't treat the foundation or design it properly, you certainly can have a breach and release a lot of energy. So I apologize. I know this is a bit of a hard slide to digest, but it's a timeline, and the intent here is to document some significant failures in the United States. There's Baldwin Hills, there's Fort Peck Dam Slide, Teton, Lower San Fernando. So there have been, in our last 50 to 70 years, some very significant dam incidents or failures that have actually caused the reservoir to be released and have significant damages and loss of life downstream. Certainly the Teton Dam failure in 1976 generated the impetus within Congress and the federal agencies to generate legislation and create a national dam safety program. Again, another slide depicting. So ironically, at this time, the Corps and the Bureau, TVA, in the federal world, they were self-regulated dam owners. So they had their own portfolio of dams. The Corps has 715, TVA has around 200. The Bureau has around 400 dams. So when you compare those numbers, sum them up and compare them to 90,500, you can appreciate that it's maybe not a high percentage, but nonetheless, those agencies have some very high and very significant dams. So again, the turning point for the dam safety program within the United States, certainly Teton was the impetus in 76. And as a result, the Dam Safety Act was developed and passed. So some other failure information to give you some context of dam failures. So this record is from 1848 to 2017. You can see the number of dam failures is over 1,500. All 50 states had a dam that failed. The state with the most is Georgia. Those states that didn't have the fewest were Hawaii and Louisiana. So again, having this sort of statistical information is quite important in terms of developing the dam safety programs. So some other statistics that came out from Stanford University in 2018 are represented in this report. Certainly would encourage you to reach out and access that information. A statistic that I find astounding is that since 1980, so in the last 43 years, there's been essentially 24 dam incidents per year. That doesn't mean failure, but there's been slides or there's been stability issues that cause some sort of emergency action. So it's essentially 2 a month for the last 33 years, which again, I find to be rather astounding. So as I said, the National Inventory of Dams was created, mandated by Congress as part of the dam safety legislation. This is the URL for that. The Corps maintains this database. It interacts with each of the 50 states. Each of the 50 states does have a legislated active dam safety program now. Alabama was the last, but last year, or maybe the year before, they did finally pass legislation and fund and start a dam safety program. So that conglomeration of all 50 states resides under the Association for Dam Safety Officials, ASDSO. The other organization primarily focused on dams in the U.S. is the United States Society on Dams, USSD, which is again affiliated with ICOLD, which is the International Commission on Large Dams. And both USSD and ASDSO meet annually. And as Alan mentioned, certainly would encourage you as you move into practice or proceed in your career, you certainly should reach out and engage with those organizations. So some statistics from NID. It's used by the National Dam Safety Review Board and Association of State Dam Safety Officials to inform legislatures in their states, to inform Congress and federal agencies to recommend dam safety policies. Many of those changes reside in WARDA legislation, Water Resources Development Act. They're not passed every year, But every couple of years, AWARDA passes through Congress, changing policies or adding new policies. So more than 65% of the dams in the NID are classified as low hazard. 50% of them are less than 25 feet in height. And almost, as I said, 70% of the dams are privately owned. Again, the privately owned dams are regulated by the state dams safety programs. And the average age of the dams are 60 plus years. So with respect to levees, this is a map from M.ASCE and FEMA showing the counties, dark green, that have levees. So there's 150,000 plus miles of levees in this country. And there's about 3 million miles of river in the United States, which again, I find is an astounding number. But again, there's 150,000 miles of levees. The Corps of Engineers is the principal federal agency associated with levees. They designed and are responsible for 15,000 miles of levees. So they're about 10%. Those that may have grew up or lived around some of the major rivers like the Mississippi and Missouri, Ohio, all can probably remember significant flood hydrologic events in your lifetime that caused flooding. So these are just some numbers. And as you can see, these damages are significant. They're not a couple $1 million. These are multiple billions of dollars from these events. The last 2017 was over $125 billion in damages from extreme hydrologic events. This is an interesting figure, again, somewhat difficult to see, but in 1927, the flood on the Mississippi generally is the event that created legislation and led to the levee construction program in the United States. And so again, there's levees both sides of the Mississippi from Minnesota clear to the Gulf. And you can see it's constrained the river and it allowed it to be operated in a very efficient manner, and certainly has reduced and eliminated a lot of damages that could have been caused from flooding. You can just see between 27 and 2011, there were over almost 17 million acres affected by flooding in 27, and somewhere over 6 million in 2011 floods. And the amount of damages that were mitigated or eliminated by the levees are, again, very significant. Congress passed National Levee Safety Act in 2007 as part of WARDA legislation 2014. The Corps of Engineers is taking the lead to implement the National Levee Safety Program. Again, the Corps is responsible for 15,000 miles of levees, and they are working with each of the 50 states. And the goal is to bolt on to the existing dam safety programs within the states, a levee safety program. So similar to the NID, the Corps has created the National Levee Database. In the last decade, they have been able to assess and populate the levee database for the 15,000 miles of levees in the country that the Corps is responsible for. And they're working again with states and other private owners to assess their systems and to get that information into the database. As I know you all can appreciate, is having this sort of historical information is the foundation for any safety program. and certainly is quite important as the organizations continue to assess the performance of their structures and make decisions as to whether they're safe or unsafe, and if they're unsafe, what sort of actions are required to bring them to acceptable levels of failure, as I'll get into here in a minute. So again, the Levee database is summarizing periodic inspections, special inspections. It also includes failure modes, which I'll get into here in a minute, and the general health, if you will, of the levees as part of being able to assess them and be able to take corrective actions when needed. So again, I find some of these statistics fascinating in that 75% of the U.S. population was born after 1960. And so I said it to Alan over breakfast this morning. So impressed with the vision of our forefathers, those that came before us in the 30s, 40s, 50s, their vision to create the infrastructure throughout the United States, a water infrastructure of locks and dams and harbors, ports, levees, hydropower. They truly had a vision for advancing the standard of living in this country, being able to increase commerce of ag products from the agricultural areas of the country through the rivers to the ports. And I say this because I say our generation, I'm not sure we've been as visionary as our forefathers. So we should all, I think, give them the credit where credit is due. And I think you, the younger generation coming out of universities such as Virginia Tech, as you go forward into practice and working on various projects, you're the next generation that can make a difference, if you will, into keeping our infrastructure operating and at a high level of safety. So again, I find those kinds of statistics rather fascinating. But again, try to give credit to the previous generations. So transitioning from the traditional view of infrastructure safety was generally fundamental engineering, strengths of materials, geologic characterization, laboratory testing to identify engineering properties of materials, and from there utilize existing materials to design dams or levees and construct them with stable slopes and such that they could handle the hydrologic and seismic loads without failure. And these were, and still are, standards based. So you're certainly experiencing all of those factors, all of those areas as you continue and progress through your education. But in the last 30 years, at least in the federal world, and it's slowly transitioning from federal to states and other private owners, we're transitioning to get to a risk-informed view of the infrastructure. So in that context, you'll hear the word risk almost universally in just about every sentence. And so fundamentally, it's a function of the hazard, the loading, response to that loading, and evaluating the consequences. As I said, in the early days of dam safety, when I was working at the Bureau of Rec, we, I think, did a good job of evaluating the potential failure modes. We might not have used that particular term, but we certainly identified the geologic conditions, evaluated strengths of materials and decided whether we needed a cutoff wall or whether we needed to grout the foundation or do some other special means of foundation treatment. And we stood on the crest of the dam and said, well, there's a lot of people down there. So, but we didn't really exert the analysis to categorize and assimilate that information as it was part of our decision making. It was not really a formal part of that. So again, as we transferred, if you will, into this risk-informed decision-making process, which is the guiding principles for our safety programs, again, we spend a lot of time and rigor to evaluate the loading conditions, assess how the dam or levee would perform under those loading conditions, and certainly we've put a lot more rigor in assessing the potential consequences. And it certainly has been well served in coordinating within the federal community and community of dam owners, but it's also been very powerful in communicating with our legislatures in each state as well as Congress in terms of defining the condition of our infrastructure. As I said, average age of dams is 65 plus years. There's over 600,000 bridges in the United States, 150,000 miles of levees, untold numbers of roads and pavement and that sort of thing. So again, the extent of our infrastructure that we all benefit from is truly amazing when you consider it's truly most of it's been built in the last 100 years of our country. So being able to articulate to the legislatures and to Congress about here are our needs as agencies like the Corps, the Bureau, TVA, we have this infrastructure, it's in this condition, we need these kinds of monies appropriated so that we can go forth and execute modifications or repairs to these structures to maintain their serviceability. So again, a very interesting graph here. This is a chart over the last 120 years from 1900 present, showing the number of dams constructed in the United States. You can see after World War II, 30s, 40s, 50s, just a tremendous amount of dams that were designed and constructed in the United States by the Bureau, Corps, TVA, other agencies and organizations. Since the 80s, dam construction with the implementation of environmental regulations, certainly it's more challenging to move forward and modify structures, giving those regulations. So I've had the great fortune, worked on the last two major dams built in the United States, Ridges Basin Dam for the Bureau outside of Durango, Colorado, and the Corps constructed Portuguese Dam, RCC Dam outside of Ponce, Puerto Rico. So again, I've been blessed in that I've been able to work on a significant number of dams around the country and around the world, and I've been able to also modify and work on several. So again, having ended my career with the Corps, I have quite a few statistics primarily focused on the Corps. So again, the Corps in their portfolio has 715 dams, almost 90%, 86% are embankment dams. The average height around 93 feet, and again, average age 65 years or so. This is just a map of the United States showing where the major dams are located within the Corps inventory. Again, the Corps has 715, the Bureau around 400, TVA around 200. FERC regulates 2,200 dams or so. And then NRCS has approximately 22,000 dams in their inventory. So Over the last decade, as the Corps transitioned from to risk-informed decision-making, they have assessed each of their structures. So you'll see this chart. This is a FM chart. So the axis is annual probability of failure versus life loss. So dots that plot above the line are pieces of infrastructure, dams, levees, locks that have high risk. They've been assessed. Failure modes have been developed and evaluated and judged by a multidisciplinary engineering team that the dam needs to be modified or the levee needs to be modified to obtain or maintain safe operation. So almost half of the 3,000 pieces of infrastructure that the Corps maintains and operates on behalf of the country, about half of that inventory is judged to be high risk and needs to be modified. So in addition to dams and levees, the Corps operates about 240 lock structures on the major river systems in the country. And again, representing a value of $3 trillion. So again, a tremendous portfolio of infrastructure. And as the Corps has transitioned, they would tell you that it's not necessarily the structure is 65 years old. It's because the major risk drivers that have been identified is just there were defects or flaws in the design, the state of practice, material technologies have changed. Concrete is air and train now with many additives. So the durability of concrete is much better than it was, say, back in the 20s or 30s. So those kinds of things. But as you can appreciate, the country's population has increased dramatically in the last 100 years. So last census, we're somewhere around 330 million people in this country. So the amount of consequences, the property and development, houses, people living behind dams or levees has grown exponentially, thereby creating the risk. So fundamentally, risk-informed methodology allows organizations such as the Bureau or the Corps to be able to rack and stack. So if you own 3,000 pieces of infrastructure, how do you decide what to work on first? So risk has been very powerful in being able to assimilate, evaluate the portfolio of infrastructure and be able to decide this is number one priority and this is number 3,000 priority. And then again, it's very powerful in working, coordinating with legislatures and Congress to be able to tell that story in a compelling and persuasive manner such that you can solicit and obtain the funding so you can go forth and maintain these structures. So again, the Corps has spent a considerable amount of effort, money, and labor hours to develop databases and be able to continue to track the condition of the infrastructure. As I said, having these sorts of statistics, this sort of information, we've been able to tell a very powerful and compelling message to the legislature. So this is just a general graph, if you will, or chart, being able to identify and depict and show a particular failure mode and is it a high likelihood and what's the consequences. Of course, red being more critical than green. But again, this, you might all view it as rather straightforward and commonsensical, but nonetheless, it still becomes a powerful tool to be able to communicate this in terms of what do you know, what do you not know, what truly try to be able to assimilate information and be able to tell that story. So you're able to tell where the source of risk is, and then through engineering, you're able to identify those engineering solutions that you're asking money for to go forth. So fundamental to any of the dam safety, levee safety programs ongoing in the country, life safety is paramount. And you'll hear it, and it may sound cliche, but nonetheless, it's truly the guiding principle. Life safety is the critical aspect of decision makers sitting at a table, evaluating information and trying to make decisions. Again, somewhat cliche, but we say it all the time in our meetings and as we evaluate structures and try to make decisions. We do no harm. So if we need to modify a structure, the principle is do no harm. Let's modify it, but let's not increase the risk during the construction period to unacceptable levels. And I think one of the great things with the transitioning to risk informed is we're now starting to really focus on systems approach. So we're thinking of the Mississippi River or the Ohio River as its own system. So we're not just focused on Lock and Dam 26 outside of St. Louis. We're truly looking at the river as a system, similar with like the Missouri River that has some very significant dams, Fort Peck, Oahe. So these are some of the largest earth dams in the world on the Missouri River. And so when we go through and evaluate them, we're truly looking at it as a system and looking at the potential for cascading failures. If, say, Fort Peck released its tremendous volume downstream, how would that impact the lower dams? So very powerful. It's very periodic and continuing. So the regulations, policy that's been developed every 10 years. So every 10 years, a dam or a levee goes through a very rigorous inspection by a very experienced multidisciplinary team. That information, again, is evaluated. Failure modes are reevaluated, and those that rise to the top as the highest risk are those that are worked on. So some of the lessons learned as we've transitioned over the last decade is many would view standards-based approach as inadequate. Problems typically have been shown to be larger than we expected. Again, over half of the pieces of inventory that the Corps manages is judged to be in need of repair. Again, given their age, that really probably isn't a surprise, but again, being able to evaluate them, assimilate them, be able to figure out whether it's a concrete deterioration problem or the valves need to be replaced or the gates need to be upgraded, again, are all very important as we move forward. And certainly, it's not always intuitive what's risky, and we have to keep reminding ourselves, certainly it's a marathon and not a sprint. And we've been able to become much more intelligent about the status of our infrastructure in this country, dams, bridges, levees, those kind of things. And I think those of us in the federal agencies being responsible for the portfolio, we definitely go to sleep at night believing that we're taking care of the taxpayers' money in a very responsible manner and definitely serving the citizens of the United States. So moving on to some of the concepts and practice of risk assessment. So it started back in the 80s. You can see this chart here where dams fall. So generally all sorts of areas were evaluated, chemical engineering, railroads, those kind of things. So you can see consequence of failure, average probability of failure was generally 10 to the minus 4. 1 in 10,000 is generally the average probability of something failing, like a dam or levee. So again, started in earnest in the 80s, certainly with NASA, the space program, and the development of rocket travel, and all of the engineering that goes associated with that in terms of failure modes, certainly brought that forward as far of other civil infrastructure. And again, 1979 federal guidelines and the 1983 Research Council was the pioneering aspect for the federal agencies. In this Dam Safety Act of 78, 79, there was specific language written that focused the agencies to start thinking in terms of risk and failure modes. So again, a lot of this has its root in the space world, NASA. And as you can see, other countries in the United States, or I'm sorry, in Britain, Hong Kong, and in particularly in Australia, those countries also began developing the methodologies and the processes that we continue to utilize. In late 70s, transitioning through the 80s and the 90s, reclamation probably led other federal agencies in developing risk-informed decision-making. The first study was done for Jackson Lake Dam in 1976 and was led by Larry Von Thun, who really pioneered the development of risk analysis along with Dr. John Smart at the Bureau. So there was a team formed and they developed the first guidelines, if you will. And Larry worked with the Canadian hydros, BC Hydro in particular, and began developing the processes where we evaluated the structures, developed failure modes, and went through a methodology to evaluate could a dam fail and start assessing probabilities of a potential failure mode. Parallel to that, we also put a lot of rigor into upgrading and reevaluating the hydrologic floods and the seismic earthquake loadings. And certainly then there was a lot more rigor put into evaluating consequences. So the Bureau has been through their inventory of 400 structures in the last 40 years. They've been through it 4 and 5 times. So essentially, they have fixed their highest risk structures in those 40 years, but they continue to monitor them through the instrumentation and through their inspection program and continually reevaluate failure modes and reevaluate the loading conditions and consequences and continually updating the risk assessment, if you will, or the risk category. So again, moving forward, trying to apply to the timeline, you're transitioning from 70s through the 80s to the current. And now if you're involved in the business, certainly the states are becoming very active. So trying to move forward, I think I'm pressed for time a bit. So again, a busy slide, so I apologize. But again, trying to summarize the various milestones along the timelines. And so trying to move forward a bit. So to give you a bit of context, what is dam safety risk? So it's simply the probability of some undesirable event occurring that would generate serious economic consequences or life loss downstream. I said we wouldn't have formulas, but here's the risk formula, which is again the probabilities of the loading, evaluating the probability of the response of the structure to that loading by the consequences. So as I said, considerable amount of energy within the federal world and in academia around the country to evaluate the loading conditions. I know those of you in hydraulic engineering, certainly the considerable amount of effort ongoing at this university with seismic research and seismic evaluations, trying to do better and get more educated on what those loads are and how structures would respond. And again, this is a typical event tree. So typically there's 8 nodes, if you will, to a typical event tree, from is there a flaw and what is the loading, and then stepping through whether that would create a failure of the structure and release of the reservoir. Several software programs have been developed, LifeSim and others, continually being developed and upgraded to evaluate the consequences. And with today's GIS technology, being able to truly look at limits of inundation from breach and quickly assessing population at risk and assessing potential life loss. Again, the rigor and the ability with today's technology to do that is just amazing. And with that, there's always uncertainty. So we're definitely always trying to assess, if we make a risk evaluation, how certain are we? What are the bands of uncertainty? And certainly factor that into decision making. So there's aleatoric or statistical uncertainty. So an example might be statistical variation in a filter boundary that you can evaluate from controlled laboratory tests. Epistemic uncertainty is, if you didn't know about it, that creates its own level of uncertainty. So those sorts of things are included in a risk assessment. So there has been numerous guidelines developed. The federal guidelines for dam safety was put out in '79 as part of the legislation. The Bureau's first risk protection guidelines came out in '97. Corps published their dam safety guidelines in 2011. And then all the federal agencies put out the federal guidelines in '15. And most recently, FERC, the Federal Energy Regulatory Commission, has issued their own risk guidelines, which are similar to the Corps and to the Bureaus. Again, they regulate about 2,200 dams in the country. So as you can appreciate, there's various levels of risk analysis, from a screening level to a moderate to a very thorough and complex, depending on what sort of decision you need to make. And certainly the more rigor that goes into it with more information allows for a very robust evaluation and very solid information for decision makers to make in terms of figuring out what structure needs to be worked on first. So again, this summarizes those 4 levels. Level 1 being the simplest, the screening risk analysis. Level 4 being the most rigorous. Sometimes, like for Oroville, after the spillway event there, to evaluate that structure to a level 4 screening took several $1 million and took about 6 months of about 30 people working on it. So it's not a trivial level of effort or a trivial amount of money when you talk about doing a very detailed risk analysis for complex structures like Oroville. The Corps and the Bureau have collaborated and developed a best practices training course. It's 40 hours, given at various locations around the country, transitioning that to USSD to be able to broaden the exposure of that training to the profession. This is from FERC. This is the different levels of failure categories that you might use as a guide when you're making your evaluations. These are, again, several categories that are used in assessing life safety as well as those economics. So again, screening level is the simplest, may take a day, may take several days. A moderate one might take 40 hours, and something like a level 4 may take several months and several $1 million. So again, it allows, in combination with standard base typical factors of safety and strength of materials, we're able to bring into play the failure modes. Are they risky? Are their loading conditions correct? And be able to make a better informed decision on behalf of the taxpayers and the citizens of the country to be able to invest our tax dollars in the most effective and efficient manner. So comparing standard base to RITM, if you can read the table there. So standard base would definitely more focused on the loading, reaction, strength of materials, stability, those kinds of evaluations. Same applies under RITM, but we're look at a wider range of loadings, and we truly do assess and try to put probabilities to those events in order to be able to rack and stack and to be able to determine which has the highest risk and which should be worked on first. So again, these are all the components associated with utilizing RITM. And over the last 20 plus years, where it's been used very in a detailed and part of the organization's operation of their infrastructure, it's definitely improved our understanding of that structure and the pieces of it, and be able to make better decisions financially and from an engineering perspective. So these again summarize the elements of dam safety risk management. You have the risk assessment and then trying to make decisions. Typically displayed in an FN chart, again, probability of failure versus loss of life. And the line there is those summary probabilities that plot above result in action. They're higher risk, and those below would be lower. So the goal is, with the expenditure of money and implementing engineering solutions, would be to reduce that risk and get your failure modes to plot below the line. So you'll hear that term quite frequently. So just some final thoughts. Unfortunately, I think in our country, particularly in my lifetime professional career, we seem to struggle as a country to develop a long-term vision, if you will, or a long-term policy. We unfortunately react to catastrophic events. Teton was a catastrophic event that resulted in the dam safety legislation, which forced federal agencies to start taking a more robust evaluation of their infrastructure. Katrina caused the Corps to look at levees and to look at flood walls and coastal protection. So unfortunately, I think we react to catastrophic events as a country and as a nation. And I think as you go forward in your continued education, as you move into the workforce and become part of our profession, hopefully you'll leave a lasting impression and be able to advance policy and be able to advance our profession to a point where we do less reaction and maybe look forward and try to do more planning. So again, tremendous amount of damage is done by hurricanes or by dam failures, levee failures, and we all need to be cognizant of that as we continue our education and again move in and be able to help everybody associated with maintaining what we have built and our forefathers have built. So some summary statistics of civil works value to the nation. So I've again impressed. For $1 that's spent by the government on flood risk management's prevented over $8 return in flood damages, reduction of that. So again, our forefathers over the last 100 years, this country has built some of the world's most robust, complicated infrastructure that we've all benefited from. And certainly as you go forward, I think you all have that responsibility, if you will, to take that on in maintaining that. So again, ASCE puts out their report card, as you can see, for 2021 for the various categories. We're not doing the greatest. So again, as Alan said at the beginning, become involved in these professional societies and these organizations. We are the profession's mouthpiece to our legislatures and to our Congress, enabled to, in order to increase our funding, to be able to make infrastructure a priority. This administration has been able to pass the infrastructure bill, which has secured funding. And so it's certainly a step in the right direction. But as you can see by our report card, we still have a long ways to go to get up to acceptable marks, I think. So, and lastly, again, I had the good fortune in my career to be associated with some phenomenal people. This is a picture of Dr. Don Deere, Dr. Skip Hendren, Ralph Peck, and Spike Underwood, who was the Corps of Engineers chief geologist at headquarters for about 20 years. So they were the consulting board for New Waddell Dam, which I was responsible for outside of Phoenix. And I was telling Alan again at breakfast, just tremendous memories of the impact that those gentlemen had on myself as a person and certainly on my professional career going forward. So best of luck to you in your education and in your professional career. So I wish you the best. Again, thank you for your courtesy and for you taking time out of your busy lives to come and listen to me ramble. So I appreciate it.